Okay. All right. Hello, everyone. Hello, everyone. Good evening, and welcome to tonight's AI Summit by School of AI Algiers. It's 8 p.m., our daily link to the AI world, where breakthroughs across industries come alive. Over the past nights, we saw AI in healthcare, different research topics, AI in production, and also a lot of topics through agentic AI, reinforcement learning, and so on. And tonight, we focus on the backbone of our connectivity, which is telecommunication, from 1G voice to 2G text, 3G data, and 4G small cells, and 5G massive MIMO. We now stand at 6G's door, faced with ultra-dense networks, sub-milliseconds, latency, semantic intelligence, and sustainability. Each evening at 8 p.m., School of AI Algiers connects us across AI domains, and tonight's final link brings us to the frontier of AI-driven telecom. It's my honor to introduce you Mr. And Professor Merouane Debbah, and allow me to present you. Since September 2023, Professor Debbah is Professor of Electrical Engineering and Computer Science at Khalifa University, Abu Dhabi, and founding director of the KU 6G Research Center. In 2023 to 2024, he served as Senior Scientific AI Advisor at the Technology Innovation Institute, integrating LLMs into live networks. He's also been professor at Central Supelec since 2007, has won over 40 IEEE Best Papers Awards, and is ranked France's top scientist in electronics and electrical engineering. Everyone, please join me in welcoming Professor Merouane Debbah for his presentation, TelecomGPT Next Generation AI Telecom Network. The stage is yours, Mr. Merouane.
Okay, thank you very much for this introduction. A real pleasure to be here. Assalamu alaikum. My talk is going to be about the topic on using what we call large language model to a vertical, which is basically the telecom vertical. I think within your series of talks, you've been going through different verticals. I just heard that you looked at the medical and health domain. And I think telecom is one of the domains basically which has the highest potential from my point of view related to basically the new revolution around generative AI. As far as I'm concerned, my name is Merouane Debbah, and basically I'm president of the AI Council. So I'm quite happy also to give the talk on behalf of all my colleagues, basically who are part of this AI Council that has been put into place in June 2023, in which worked quite hard into publishing what we call the National AI Strategy, which was announced the 7th of December, basically 2024. With basically some different, I would say, kind of proposals about how Algeria should conduct its vision related to AI. If you want to contact me after the talk, my email, as you can see, is there. And of course, I'll be more than happy basically to support many of you in their journey related to generative AI. Something particular to what concerns me is, of course, that I've been working mostly at the interface of academia and industry. And for people who know me, I've been moving back and forth years, either for a couple of years in academia as a professor and director of research centers, and at the same time going back to industry with executive positions in companies such as basically Huawei, where I was vice president of research and also basically Technology Innovation Institute. And of course, my topic of research has been at the interface of mathematics, signal processing, AI, and of course, 4G, 5G, and now 6G systems. So, a lot of the things that I'll be talking about can be found in a series of papers that I strongly encourage you to read. That you can, of course, find in archive. I tend to put all my papers on archive because I think that's the best way for all of you to get hands on freely on basically the latest information. And so if you go on archive, which is basically the repository where all the researchers put their papers, and you type my name, then of course, and you can find the papers which I worked on with my colleagues related to the topic of applying large language model to basically the telecom sector. And here you have a bunch of them related to that. Related to the LLM, I didn't mention it, but I've been working since more than 3 years on a couple of large language models. One called Noor, which was the first large language model in Arabic released in 2021 with 10 billion parameters. I've been working also on one other model called Falcon, which was basically one of the top open source model in 2023. And also quite recently in Algeria, in collaboration with basically a startup called Tamatek, working heavily on a large language model, basically related to Darja, which is called Hadratna. So if you have time, I strongly encourage you to look at those basically models and get back more information. Okay, so let's start a bit the topic today and understand what's this link between the telecom sector and AI, and why now I'm working more at this intersection since basically 2 years. If you have no knowledge about the telecommunication sector, you have to know that they've been going through what we call generations of mobile communication systems. In 1990, we started developing basically a system which was tailored for what we call mobile for voice, meaning having a network which provide seamless communication with mobility, with the intention to provide voice for that. And in 1990, we started deploying that kind of system, which was called 2G. In Algeria, 2G is still there, by the way. And one interesting thing about it is that the KPI, which is what we call the key performance indicator of 2G, which is mobile for voice, has been, of course, brought through several technologies. One of the most known technology for 2G is called GSM, but you have to know that there are other technologies like IS-95, for example, which provide 2G. 10 years later, because these generation are in the 10-year time frame, we decided to deploy 3G, which basically provide mobile for data, the capability to download or upload basically data. And many of you had these what we call 3G dongles that you put on your computer with USB, and with which you could download and upload related to that. 10 years later, in 2010, we started deploying what we call mobile for internet with 4G. By the way, same here at each case is that behind 4G, there are several technologies which provide 4G. Typically, one of the most known technology for 4G is called LTE, long-term evolution. But you have another one which is called WiMAX, for example, which also provide 4G for information. And 4G was tailored to provide what we call a wireless ADSL experience with mobility, what you had indoor in your house to get it in an outdoor in a seamless manner. You have to know, by the way, that people who developed 4G were so focused on mobile for internet that when we deployed the first 4G systems, phone calls were not working that good. Why? Because voice in a 4G system is basically an application, whereas in 2G it's technology. And if you had the ability to understand how voice over IP works, it turns out that we are not able to provide that kind of latency requirement that you're quite used to. And you have to know that the majority of 4G systems that we've been deploying starting 2010 had basically a system called CS fallback, which means circuit switch fallback, which basically tells you that whenever you make a call, you browse on internet on 4G, but when you make a call, you go on a 2G, 3G systems. However, by the years 2016, 2017, we realized that we cannot cope with having a lot of legacy systems to continue to that. And why I'm mentioning that, because it turned out that AI was a key enabler to provide basically something related to AI-based voice over LTE, which enabled basically the performance to increase thanks to the AI, I would say, kind of technology behind that. I'll talk about it afterwards if you're interested, but you have to know that in general, when you start to optimize or try to solve a problem, it tends to be quite difficult because you need to model it. And in general, a lot of the networks, especially when you want to model end-to-end systems, they tend to be very complicated. And it turns out that that was a good example of what we call a data-driven approach, in which instead of trying to model the end-to-end performance of a voice call on an internet system, which is very difficult, we ended up by, of course, gathering a lot of data and using techniques related to reinforcement learning to improve the system. In 2020, we started to deploy the first what we call 5G systems, which were tailored for mobile for things. In Algeria, as you know, a couple of weeks ago, announcements were made basically for a new generation of mobile systems called 5G, which is going to be deployed. You have to know, unfortunately, that the majority of 5G systems that we've been deploying around the world do not really provide mobile for things, but just providing what we call an enhanced mobile broadband features. And one of the reasons that we're not still capable of providing the feature related to ultra reliable low latency communication, but also basically the feature to massive machine type communication, is that a lot of operators are not still able to make money out of things. Starting this year, we start seeing a bit of change in how the business models are turned around, and these are going to come more and more in the future, basically with the evolution around 5G. And one of the things we're targeting by 2030, in which I'm implicated a lot, is basically the kind of network that we want to build for the future, which is what we call mobile for intelligence. What do we mean by that? Is that we're starting to see basically AI being more and more pervasive, meaning at each point of the network, and in which basically we're not starting to see humans or things communicating between each other, but mostly AIs communicating with each other, or what we call agents, for people who are familiar with that kind of terminology. And of course, when you look at that, the question, of course, arises that when you start deploying a network in which AI start to talk to each other, so typically, as an example, having ChatGPT talking to another ChatGPT, the question that arises is, are the actual network infrastructure that we have built so far adapted or providing the full potential for these AIs to talk to each other? And it turns out that definitely it's not the case. And I'm going to give you two examples on why it's not the case and why we need to build an infrastructure to connect basically the intelligence together. The first one basically is related to a topic called semantic communication. And I'll give you just a very good example to illustrate this notion of semantic communication within the realm of basically AIs. If you have basically a generative AI, and typically let's take a ChatGPT model on one side of the network, and you have another ChatGPT on the other side of the network. And suppose you want to send a video from one point to the other point. In a classical network, what you would do, you would take the video, you would compress it, zip, for example, and then basically send the compressed file. On the other side, you would take the file and then decompress it and get the data. Now, if you have AIs on each side, and typically let's use ChatGPT, one way to do it would be very easy. You would do video to text. You will not send anymore the file. You'll just send the instruction or the prompt. And on the other side, what you would do is text to video. So with this system, I showed you that LLM are what we call super compressors. And so you could use these AIs to transmit data on a network very efficiently by just basically doing video to text, image to text, and then sending it. However, if you do that, and you could implement that, by the way, already today on a 5G network, on a 4G network, on internet, on Wi-Fi, you have a certain number of caveats. The first one is the end-to-end latency that you need to guarantee. If you do text to video, it would take you an hour basically to generate the video, if not more, depending on the length of the video, which is not compatible with the communication systems that we have, on which with a DZIP file, you would get it quite immediately. The second is, if you do video to text and you would need to define what would be that text. Would it be English? Would it be Arabic? What is the kind of universal language on which you're going to do to make the AIs communicate? Why would AIs communicate in English, by the way? There's no reason. If you want to communicate efficiently, they could construct their own type of protocols to communicate. But if you do that and you do video to text and text to video, you'll never get the same video. And I think some of you have tried using these tools. If you prompt basically ChatGPT and ask a question, you'll get an answer with a certain formulation. But if you ask the same question in 2 hours, you'll get the same answer, but not the same formulation, which means that the meaning is conserved, but not basically the perfect reconstruction. But when you think of us as humans, when we talk, it's quite similar in that way. What I mean by that is if you ask me a question right now, with big probability, I'll be able to give you an answer with a certain formulation. But in 2 hours, I will give you the same answer, unless I'm a bit crazy, but not the same formulation. So in some sense, we're able to have a common understanding between different AIs, but the notion of perfect reconstruction has to change. So if you want to build a network on which AIs have to communicate together, you would need to standardize a bit the interfaces and look at the notion of how you conserve the meaning when it's transmitted so that there's a common understanding on both ends of your network, but not perfect reconstruction on which are built on networks. So this just gives you already an example on why basically when you want to connect intelligence, the network that we have built so far is not tailored for that kind of systems as if today. The second thing also is the arrival of what we call AI agents. Today, a lot of the network that we have built, and especially the phones that we have built, are based on the notion of stores and app stores on which people have applications. And we have been able basically to build a whole system with apps on top, basically with this OZ layer. But if you think about it in the field of basically agents and AI agents, why would you need an app? There's a big probability that in the next 2 or 3 years, the notion of apps will disappear and the notion also of app stores will totally disappears. Today, if you want to book a car, you would download a number basically of apps, call them basically Uber, call them basically Kareem, call them basically whatever you want. You will take basically the app, you will then type basically the kind of destination, and then you'll have a car coming. But the notion of agents, you don't need that. You just need to say, I want a car in 5 minutes down my house. And that kind of instruction will convert basically your conversation into an action, which will go, which means that the future basically would just be an operating system in which you talk. And basically you have that kind of execution which is put into place. Now, if you look at how these kind of things scale and the number of agents which are interacting, because you're going to be talking with an agent of a car, which will basically start doing a transaction, it also changed the way we have built basically the network with marketplace on which these things are happening, rather than have app stores and things. So these two examples already show you quite rapidly that the notion basically of network that we have built so far is not tailored for a system where we have AIs which are massively deployed at each point of the network and which connect to each other. Now, all this happened because in 2023, two things happened. The first one is what I call the GenAI revolution, which I'll talk about and present quite rapidly for you. And then the second basically was the fact that 6G kickstarted. And these two have now converged into a point where we're seeing great potential basically on the convergence of communication and computing with this revolution that is happening right now. So if you have no knowledge about GenAI, I think this example will kickstart quite rapidly the notion of GenAI and understand better how all this came in and what's behind the roots related to AI. So in this example that I'm giving here, you have basically two pictures. One, and this is a classical example that I give for people just to introduce the notion of basically data-driven approach versus model-driven approach. On the right side, you have what we call a guy called Newton. I think all of you are familiar with basically what we call the Newton equation. And on the left, you have something quite also familiar for you, which is what we call a ballistic kick, meaning you kick a ball at a certain distance. And in general, at the age of 18, especially in Algiers, at the age of 18, where you pass what we call the baccalaureate, you have a classical question, which is, give me the angle theta with which I need to kick the ball at a distance of 100 meters? So this is a very simple question. And in general, basically, what you do is you take what we call the Newton equation, which tells you that m times acceleration equals gravity, m being the mass of your ball that you're kicking. And you integrate it 2 times, and then you can find basically the parabol and the angle theta with which you need to kick the ball at a distance of 100 meters. Now, having Newton is not an easy task because it requires to have basically a model of how cinematics goes in, which requires many years basically of research in general. And in general, you have pressure to find basically a solution to your problem. So in this case, on the left, if you don't have access to Newton, what would you do? Well, basically, this is what we do in medicine, that's what we do in other disciplines. You do what we call a data-driven approach, meaning you kick the ball like hell. So you kick the ball many times and you put in 2 columns, distance versus angle. I think this is quite clear. And next time you're asked to kick at 100 meter, you'll look basically in your database. This is called a lookup table. If the distance 100 meters is there, and if the distance 100 meters is there, then you'll find the angle with which you can kick the ball. This has nothing to do with the AI. It has nothing to do with machine learning. It's called data mining, where you find a number in a database. So it's like a mine where you're going to be looking at a certain number. Where it gets interesting is when basically the number is not there. So if 100 meters is not there, but you kick the ball at 95 meters and you kick the ball at 105 meters, then it sounds quite basically intuitive that 100 is a linear combination or a mean of 105 and 95. Clear? And so what you're going to do is look in the angle domain, what kind of mean or regression you're going to do in the angles to find the angle. What you're going to do is learn, and this is where we talk about machine learning, how to relate basically the column 1 with the column 2. How you're going to learn the function that relates x to theta. So if you call theta is equal to f of x, you will learn the function f that relates x to theta. So you will do some kind of learning algorithm which enables you to learn that function f. Now, how do you learn a function? This is not quite easy in general. So if the function basically is quite general, what we do in general, we project it in a basis. Clear? So if you go back to school, if the function, you don't know it, one intuitive way of learning that function is not to learn that function, but learn the weights of that function in the basis. Okay? So what you would do is say f of x is a polynomial expansion, a Taylor series. So you'll say f of x is equal to a0 plus a1x plus a2x squared plus anxn. Clear? N will be the degree or the size of your polynomial or the size of your model. And a0, a1 to an will be the weights of your model. And learning basically the function translates only to learn basically the degree n and the weights. And how you do that, you minimize a certain error. You take all the data that you have and try basically to fit it to the data set that you have been kicking the ball with. Once you did that, then it's easy. Anytime you have a new distance, you just apply it to your polynomial and get basically what you learn. It turns out that doing a polynomial expansion turns out to be quite complicated in terms of learning and how you do it. One way to do it is also to project it in another basis, which will be a hardware basis. We call this a neural network, in which basically you have weights and a certain number of layers. And in the same sense, you would be learning basically those weights, but on a hardware architecture, which is called a neural network. What's fantastic about neural network is that you can show that you can learn nearly any function you want up to some conditions which are very mild in the system. And so you got nearly the idea. What you do is that you have a neural network. It's a black box. You have distances and angle. You put them back and forth on each system. And then you learn basically those weights and the degree of your polynomial. And next time you have a new distance, you put it in the box, and then you can be able to get the angle. And you have been able to do what we call the learning of that function through a machine learning algorithm to do it in a very nice manner. So what I showed you quite fast is that with this technique, You can replace Newton equations, you can replace Maxwell equation, you can replace Schrodinger equation, you can replace nearly any theory you want. It's quite magic. And the story is done. Uh, Said that, if the story was done, then we would have solved everything. In fact, there are a couple of caveats, which makes, of course, the things more complicated than we thought. The first one is you need a lot of data to be able to learn how to kick the ball. Meaning that suppose that you kick the ball many times when there was no wind, but the day you're asked to kick the ball, there's wind. So it turns out that obviously whatever you learn is not working anymore. And so you need basically to kick the ball when there's a wind of 5 kilometers an hour, 10 kilometers an hour, 15 kilometers an hour, which of course explodes the number of data sets that you have. Of course, you can always use some techniques called transfer learning, which are based on the fact that if you learn there's no wind, when there's a bit of wind, you're not too far off. You need a bit more data, but not too much to continue. But you still need a lot of data at the end because you need also to transfer that learning in various databases. To go in a very easy manner, it tells you that if you learn French, then obviously it's much faster to learn Spanish because these two bases are correlated. And so you could, of course, speed up the learning, but you still need a lot of data to continue on going in all directions. The second, which I think is more complicated, is the fact that I went a bit fast by telling you that there was a one-to-one mapping between distance and angle. In fact, it's wrong. You need to have x and v0. I don't know if you see the arrow that I'm putting, which relates to theta. You need three columns: x, initial speed, and theta. So it was not obvious that theta is a function of x and v0. Clear for everybody? And how you know it, it's not very easy. And so in general, knowing which columns you need to put in your problem requires a bit of intuition on what we call the domain expertise, which tells you that in general, to be able to come up with some solutions to some problems, you need to have experts who know very well the domain to tell you which columns you need to put so that you can find the relation. To give you a very simple example, it is as if you were in a hospital and you have a doctor which recruits you. You come from the École supérieure d'informatique and tells you, okay, you have one column called cancer and one column called temperature. Now I give you a new temperature of a patient. Tell me if he has a cancer. It seems obvious for you that you cannot relate basically temperature to cancer. The question is, what are the new columns you need to put? Blood pressure. So you have three columns. You start doing it, doesn't work. And finding what are the columns you need to put within your problem becomes a very cumbersome problem because it explodes the number of combinations in some sense. And so this is, I think, very tricky in many cases. And the third caveat of this technique, which makes it not universal, is that whatever you kick on Earth, you'll never know how to kick on the moon. Why? Because, of course, gravity is very different on the moon. So this is called generalization. This has nothing to do with AI. It has to do with, of course, the techniques that we use today to do the kind of learning, which are based mostly on techniques of linear regression that I was talking about, and for which basically you're not able to discover gravity from your data. Clear? Now, of course, if you want to discover gravity from your data, you need new techniques of machine learning to be applied on that, which are mostly of the topological nature, meaning that to discover gravity is an invariant of your data, so it doesn't change by rotation, it doesn't change by translation. So we need to apply some kind of mathematical tools which are able to discover what are the invariants of your data, which are mostly topological structures that you need to discover. You have a lot of mathematicians, even in Algeria, working on that topic, trying to discover this kind of invariant, but we're still far off in being able from any kind of data to discover the theory of that. We're able just to discover what we call the approximation that we can do, but we're not exactly the theory. And this, of course, reduces the scope related to that. I think with this example, sorry for taking a bit of time, you understood the basis of what we're doing. Now, for this problem of kicking the ball, before 2017, the majority of people were using what we call NLP techniques, what we call natural language processing, which is not specific to language, by the way, but basically it started with language in which you needed to predict basically some words, and they're based basically on statistical rules that are based on correlation, where you use something called bag of words and word to vec, where you put the queen is something related to woman, a man which is related to a queen, to a king, and you go on like that. And these techniques of NLP were based on hardware architectures of neural networks, which are quite known in literature, which are called RNN, recurrent neural network, LSTM, GRU. One of the big caveats of these techniques before 2017 is that they were mostly sequential and not parallelizable, which makes that learning takes a lot of time because you need it every time to go one after the other. By the way, this is a general concept in science. Is if you have something which is sequential, then basically in general it's not a good idea. You need good idea is always an idea that scales, meaning that if you have, for example, even not in science but in business, if you have a business that can work with one customer, two customers, but whenever you have 10,000 customers you don't know how to handle, then it's not a good business because it can't scale. And so one of the caveats that we had with all this structure was, of course, the scaling. The second is basically the fact that they failed in long sentences and you could not learn long dependencies. And I think if you're familiar with basically tools like ChatGPT, you realize how you can cope with that. And so in 2017, an important paper appeared called Attention is All You Need, and in which basically the authors, which come from Google Brain, Google Research, and University of Toronto, came up with an architecture which solves this problem that we're talking about, which is the parallelization and learning long dependencies. They propose in that paper an architecture which is called the Transformer architecture, which is at the heart of what we call the GPT, which means Generative Pre-trained Transformer. Now, a lot of people put basically the GPT in relation with ChatGPT of 2022. ChatGPT in 2022 is only the interface or the chat version. For people who are in the topic, which were 5 years before, a lot of people were already working on that. And I think it's quite important to highlight that GPT-2, GPT-3 appeared before and people were working on that. And the chat and became very known only because basically, of course, it started to have that interface on which people could start working on. But now, how is this GPT related to basically what we call large language model? What is the relation between LLMs and the GPT type of architecture? Well, it's all about how you learn what we call a conditional probability distribution. So in this example, you have the capital of the United Arab Emirates is Abu, and I need to find what's the next word. And in general, when you write on ChatGPT, you realize that what you need to do is just complete the text. When you ask a question, it completes the text. And so if you were able to know what is the property that X is equal to anything, knowing that the capital of the United Arab is Abu, then what you would do, you would calculate all those probabilities and put the word. So your property that X is equal to Algiers, knowing that the capital of the United Arab is Abu. The property that X is equal to Paris, knowing that the capital of the United Arab is Abu. The property that X is equal to Dhabi, knowing that the capital of the United Arab is Abu. You would look at all those probabilities. You would take the most likely, and then you put it. Clear? Once you put it, it becomes a context. And then you predict the next word by taking also the most likely. So by taking the most likely word at each iteration, you're able to complete a whole book in that sense, if you were able to know that conditional property distribution, which is nothing else than a function. Clear? So the whole problem boils down that if I could know the conditional property distribution or learn it, then basically I could be able to complete any text I want by just coming back and forth. Of course, doing that has some consequences which are called hallucination, in the sense that if you make a mistake, because it's probabilistic filling at each time that you do, if you make a mistake on one, then of course, then your whole text becomes wrong. It will be much better than predicting the next word is to predict the next trajectory, x1, x2, xn. But then, of course, the computational cost will be quite huge because it would need that you'll take all the different sequences which are possible and calculate them all, which of course explodes the kind of memory that you have in your system. So in general, we do it just word by word. And in general, we don't even do it word by word because the notion of word is ill-defined. We will do it what we call token by token, which is basically the least representation of an alphabet. And why? Because a word by itself is ill-defined. An alphabet is also ill-defined. You will need to do a representation. For example, alif can be written in Arabic in different ways. And so it tells you the way that you need basically to take a text, convert it into basically a certain least representation of the alphabet so you can do it. So the whole problem, of course, boils down to knowing the conditional property distribution. But how do you learn a property conditional distribution? Well, we said, how do you learn a function? You project it in a basis. You could project p of x in a polynomial, a0 plus a1x plus a2xn. Take all the data that you gathered and learn those coefficients. I told you before that doing that does not scale. Doing it with an RNN architecture is not good. And it turns out, of course, that if you want to do it very efficiently, it turns out that the GPT type of architecture or the transformer architecture turns out to be good. And the second thing I didn't mention also is that in that paper, not only they do the transformer, but they also show that the system can be what we call a self-supervised problem. You don't need to label all your data. And so if you go on in the way things are built, you take basically your text, my name is, you do a tokenizer. So the tokenizer is at the heart of representing your thing. And so the way you tokenize is very important. You do something called an embedding. You go through transformer architecture plus an embedding softmax. And then you go through your sampling and then you predict the next word. And then you go on and you do it again. The majority of people who are building basically today LLMs are basically using this kind of approach that I told you about, which is basically a encoder type of approach for doing these things. Now, of course, you tell me, oh, if it was so easy and you're explaining it this in a very easy manner, why don't everybody, or why not everybody's jumping in? Well, the main reason is that it costs money to build these things. So it doesn't cost money because you have to do it like that, but it costs money because in general, you need to buy what we call GPUs. You need to run them at a scale which is quite huge. And so in general, it costs a lot of money to build those data centers, and it requires also quite sophisticated skill to run basically this GPT architecture on such a big amount of GPUs. And it tends up to be what we call engineering art in how basically you parallelize basically that training to make sure that basically you can run it in an efficient time. And here you have typically the cost that has been going on from basically GPT-3, GPT-3 with 175B. The 175B means the billion parameters, which was roughly $9 million. Llama 1, as you can see, 65B, 65 billion parameters, which is the size of the model at $4 million, to Croc 3, which was basically announced in February this year, finalized at least in December 2024, roughly $1.2 billion. So very few, basically, companies or institutions can afford to do that. Of course, the majority of people today, what they do is they take these models and in general, they fine tune it, for which the cost is much more reduced related to that. By the way, the DeepSeek era does not change anything. A lot of people tell me that, with DeepSeek, you don't need that much money. Well, it doesn't work like that. The way things work in the domain is that whenever there is a company or an ID that came up with a new technique to make things more efficient, we just take those more efficient techniques and then run it on the 100,000 basically GPUs to even scale and go much further in how we do it in the way things are done. Okay, so that was for the first part, which is basically related to this 2023 GenAI revolution. The second thing was basically the kickoff of what I call the 6G race, meaning basically this definition that we wanted to come up with, basically with KPIs, key performance indicator, on how we build a network that connects basically the future of the intelligent AIs. Well, basically, it started roughly before, but in 2023, what was good is what we came up within the ITU with the definition of what we want basically by 2030, which was called IMT 2030. And the same year in December, There was also a gathering of more than 150 countries in Dubai to start discussing the kind of bands and frequency with which it came. What's interesting is that we came up with what we call the metrics, which we want to build that kind of structure, which relates to basically an end-to-end latency of roughly 0.1 millisecond, a data rate on which these systems are going to be communicating at roughly 1 terabyte wireless, and also some metrics related to the number of systems that are connected to each other, the kind of energy efficiency that you can build. And basically, these things, of course, have been also timelined with some goals related to when they will appear. And one of the goals is, of course, to have all this happening by 2030, which is quite important, in which all the actors are working quite intensively to start building basically the standard to build these things. By the way, we don't standardize AI. We standardize the interface on which you talk to each other. So in general, you don't standardize basically your intelligence, but you're going to standardize basically the communication protocols to make two systems talk to each other. And standardizing those protocols is very important, because it's like humans. If you want an Algerian to talk to a Chinese, then you need to standardize basically what is the language they're going to be using to discuss together, And so the Algerian is going to convert his language into English, the Chinese to English, and then talk to English, because we think English is some kind of universal language, or is there something else to be done? And especially also the kind of synchronization they need to do, because the background knowledge is not necessarily lame. So I give you ChatGPT talking with ChatGPT, but it could be basically a Claude model talking to a DeepSeek model, typically. And both are not trained on the same kind of background. And so there is a certain point where you need to go one step forward. Now, for doing that, of course, a lot of people are working intensively on the technologies behind. These can be wrapped up in three categories. One is related, of course, to providing the rates on which these systems are going to be communicating very fast. And this is what we call broadband connectivity. You have here a list. If you're interested to go much further, I'm quite a specialist of a couple of these technologies, especially on OFDM, holographic MIMO, typically in large intelligent surfaces, but they're roughly basically, I would say, more physical layer approaches. The second is related to what we call sensing and control. And sensing and control means basically the capability of the systems to start basically being able to see the environment and basically interact with the environment. Same thing, if you're interested, I can go. But what I'm going to do now is mostly focus on the third one, which is related to intelligence, on which we have been now building some kind of the building blocks related to the AI transceiver, multi-AI generative AI, and AI generative AI, distributed GPT, and learning semantic source code and semantic channel codes. Now, my talk was about TelecomGPT, which relates to the last column. How is this thing related to basically the last column? TelecomGPT pillars are related to three categories on which I'm going to now focus on, which is basically the first one, the will for the telecom sector to start building telecom foundation models, which can be embedded in devices. And I think this is quite important in the sense that we are now having phones, we have also IoT device. And the question that arises is how you bring all these LLMs that we have built so far and make them run into smaller and smaller systems, considering basically that these are very big models and basically the kind of energy efficiency, the kind of consumption, the kind of course of complexity that we can embed in those devices is reduced. So this has opened the door to a lot of research at the moment. We have two approaches to go towards that. One is to take those big models and quantize them. So you quantize the weight and make sure basically that the overall, I would say, size of the model fits in your device or your IoT. In general, by quantizing them, well, basically you reduce a lot of performance. And so in general, you need to make sure how to make tiny models being run. Second is, which is the right approach, but is a bit complicated, is to take into account that you have low precision in your device and you want to build basically low precision AI models, which in a sense tells you that typically the weights, for example, can take only binary values, 0 and 1. They can't take more than that. And then basically you need to build models for which basically the weights can only take 0 and 1. This, of course, opens the door to what we call binary neural networks. This is a harder topic because basically today the majority of the learning mechanisms are based on the fact that you need to optimize. Optimize requires a derivative. It requires then a gradient descent. And this is at the heart of what we call the stochastic gradient descent that is basically at the heart of all the systems which are used. Now, if you cannot do any more a derivative because you're living in a discrete space, because the weights can take only 0 and 1, then basically you need to relook at the problem of optimization as combinatorial optimization. And if you do combinatorial optimization, then the gates are quite open to all techniques that you need to come up with on how to solve that. So this is, of course, opening a lot of research and how we are able to make sure that in the future, we have AI, which is basically ubiquitous in each point. And for that, we need to make sure that it can be ported in an easy manner in all the devices. The second thing is that we don't want to build anymore the LLM in some in sense of language. In the realm of telecom, we're talking about what we call multimodality. Okay, we have, of course, language, text, we have images, we have voice, we have radio frequency signals, we have pressure, we have a lot of information that these IoT devices are bringing in. How you build basically the future of the LLM for IoT is a big question, in the sense that in the future, we want all the devices to start talking to each other. Okay, we want basically a table to talk to you. You can talk to the table by any kind of discussion you want. When you put your hands on the table with the IoT, it senses the pressure and then it gives you some feedback, and so you can start interacting. And this, of course, is totally open because how you tokenize typically radio frequency signals is a bit a headache. For example, in our case, we've been working on RFGPT. So RFGPT is typically the idea of I want to measure some signals, and from the measurements of the signals can tell you what I'm seeing. This is not new. It's related to what we call radar. But imagine that you can just do RF to image, and it gives you what is the plane that is coming and in the air. And so this opens a lot of doors on how you do it. And the last one is, of course, building the architecture on how these basically agents are talking to each other. And so in our work, what we did is in 2024, we started developing basically the TelecomGPT era, which is the first one, in looking at how basically not making models small, but just building a not a multi-model, but just a unimodal model for the telecom sector. Why the telecom sector? Because a lot of the things that we build when we build telecom are not tailored for the telecom domain. All the models, when you start asking questions which are very precise, they are not able to answer. So what we did is start trying to understand how we build that. And so if you're interested, you can read our paper called TelecomGPT, a framework to build telecom-specific language models. And the idea was to build a data set for the telecom sector, build a benchmark behind that, and also a training pipeline to be able to do those things. So we scrapped all the data that you can imagine related to the telecom sector coming from various sources, from 3GPP and others. We did the extraction and pre-processing, and then the task specification, data creation related to that. And so if you're interested on how you do, you take the general purpose LLM because you're going to fine tune it. And by doing that, of course, you're going to get better performance than the general purpose LLM. You take the telecom data set that you prepared, you do some instruct tuning with supervised tuning, your alignment tuning to get your telecom GPT. And of course, you define also the kind of evaluation that you want to do for that model. Clear? What do you do with that? And so here are a couple of examples to showcase the performance of such a fine-tuned model, which is very helpful for the industry when they're using it. So the first thing that you can do with that is basically just knowledge search within your company. You're asking some terminologies that you don't understand. So typically you ask, well, what does IM stand for and why is it considered desirable for constellation and communication systems? And then Telecom GPT tells you index modulation is desirable for communication system constellation due to its higher signal to noise ratio, and gives you quite detail. Second, in general, you want also that to help the assistant in your domain. So you have all the data. For example, you work for Mobilis, and you are in the field and you want to understand basically when you're in the field how this process works. So here typically you have a question, describe the process of providing authorization to a mobile device for pending this transaction request, and it tells you to provide authorization to a mobile device for pending transaction request, and it gives you all the detail. And then you want also to activate some kind of functions for which you're not sure. So typically initiate event-based charging with decentralized and centralized, you need determination, centralized rating, and it tells you all these things. Of course, you can add on that voice, because in general for the technical field, you're not basically able to write and you want to ask the system, well, should I put cable red or cable green in the base station at the moment, and how you do it. But you could also go one step forward and have an agent which executes some tasks which are not manual, so it does exactly the code. Third thing is also, of course, a lot of codes in the machines that you don't understand. You ask, analyze the script's contribution to a telecom workflow, specifying its primary functionalities. And it tells you exactly, because we've been training in a lot of code related to telecom. The script defines a function BSC in binary symmetric channel within the telecom domain. It takes input splits, as you can see, and goes forward step by step. You have also the capability also generating code specific to your domain, which is very important, because then, of course, it increases your productivity. So typically here you have develop a C function, develop a Python function, develop a MATLAB function, whatever, that retrieves and returns the transmit power value for a wireless device. The function should update a data structure, and then you go on like that, and it tells you on how you can go step by step. And one last example that we did also is to help also people like you to write reports, to write papers, where you can just write what you want, and then all the equations are filled in your paper. We took a paper and took off all the equations of that paper and said, well, please fill in the missing mathematical equation represented by mask, placeholder in the provided section of a telecom relevant research paper that basically deals with the system model or problem formulation. And then, as you can see, we say we consider a discrete time zero mean jointly proper Gaussian fading channel with the following input-output relation replaced by mask. And you can see as a response, he was able to find back that it was y equal hx plus n, which is equal to x h plus n. If you go to the last line, we say its variance is given by blah. For mathematical reasons, we assume that the autocorrelation function RS is absolutely summable, and we put a mask and he's able to find it. So that's quite interesting, because also in this case. Now, of course, on that, we've been working on other modalities like images. Typically, one of the things that people are very fond of in the telecom domain is that, in general, in your house, your Wi-Fi, for example, does not work. It starts blinking. And so what you want is just take a picture of your Wi-Fi box and say, tell me what's happening. And then it does some root cause analysis and tells you what you usually do when you call the operator, and tells you what are you seeing, and he tells you, okay, do this step, take off, and goes step by step. So by adding some other modalities, you can do much more sophisticated things, and we've been working on that. You can do it also in different languages, not necessarily in English, because a lot of the data for network operators, typically like mobilis, is related to Darja. We have a lot of documentation, a lot of discussions which have been trained on, and on which you can build these kind of things one step forward. Second step that we've been running in is, of course, building more modalities in it. And as I told you, more modalities is basically taking what is very specific to the realm of telecommunication. One of the things which is very specific is basically the realm of radio frequencies, which RF signals, which are basically measurements that the wireless network does, and in which you want to do what we call sensing. So what do we mean by sensing? We take a lot of channel measurements related to some topology, and a lot of basically images, 3D images, which represents that topology. Because remember, the RF signature is nothing else basically than a signature of the environment. And so we started basically training a VLM, visual language model, related to this different data set. It turns out, of course, that doing that is in general not enough, because basically you cannot do all the measurements, and you need to resolve to what we call synthetic data. What I mean by synthetic data, meaning simulators, which are able to do techniques like ray tracing, which builds basically a lot of data set. By the way, today, This is now mostly the classical methods that people are using, meaning they're using a lot of synthetic data, either through these ray tracing techniques or through what we call digital twins, which are able to build basically more data for you to start learning on top of what you're doing. And we've been working on that, and you can check the paper and looking at basically the capability of from the image to provide you the RF signatures, but also from the RF signature going to the image, which we call signal to image and image to signal. And this is typically what you want to do in general to be able to do what we call 3D reconstruction. 3D reconstruction meaning that you do some measurements and you're able to say, hey, what's happening in my house, for example? Is there somebody? So imagine you have Wi-Fi measurements, and those Wi-Fi measurements are able to tell you what's happening in your house. So from measurements, you can say, is there somebody who came in, at what time he came in, and all these are information that the IoT systems is providing you. And the last one on which we are still working on is, of course, basically what we call the Telecom AI agent solver. And here the idea is, of course, to build up a system with the different functionalities and look basically where all the different functionalities should be, either at the mobile, the base station, at the edge, and how these things interact so that you can specify some functions that you want to be able to optimize your network. So there's a series of paper that we built quite recently on looking at how we are able to optimize the systems. As you can see here, I strongly encourage you to read them and provide you a bit of the idea on how to go forward with that. And the idea, of course, is that you want to build an autonomous network management where you just provide, as you can see here, as the system, configure the eNode B in FDD band. You just say basically what you want, and then it executes by optimizing the system with the different inputs and gets you the right beam, the right tilt, and things like that. And these are things on which we are working on. We had a demo with the team, which had worked hard, and in combination with a startup called Merouane that was done during the last Mobile World Congress in Barcelona in March, in which we showcased some of the features that can be done using this approach of basically agents and basically how you execute the systems. And we've been also looking at several examples on how, by providing some instructions in terms of reduction of the energy consumption of a network with some goals targets, how the system can interact and be able to go one step forward. I think the future is going to be, of course, much more around these telecom AI agent solvers. By the way, this year is the year of the agents, and how you can bring them basically in providing you this autonomous network management systems that we've been talking about. Okay, I think you got an overview of what we're doing today within this convergence of, I would say, the telecom domain and the AI domain. And I gave you a couple of examples related to TelecomGPT-1 that we started, TelecomGPT-2, which is the multimodality and what we call the LLM of IoT, and the TelecomGPT-3, which is basically providing the capability of building autonomous network management systems with AI agent solvers. Happy, of course, to answer your question right now. And I think I hope it was also interesting for you to get an insight on how we're dealing with this vertical today with LLM and telecom.
Thank you so much, Mr. Merouane, for this very interesting presentation. It was really inspiring and really interesting talk. Now we open the door for questions for the audience. Feel free to ask your questions and get benefit of this opportunity to ask the Professor Merouane about anything related to the topic. So we have the first question here from Mohammed. He said his question is about companies are not profitable yet. So he's talking about companies that could be have profit from Telecom GPT.
So two questions. There is today, of course, a big issue in making money out of AI, and so in general today, irrespective of Telecom GPT, the whole sector is not really making money. They're burning more cash than making money. I think In the realm of really making money, maybe OpenAI is still unclear, and DeepSeek are maybe the two ones which are making a bit of money. The others are not. And I mean, one of the main reasons is that the cost of training those models is still going much higher than the money which is driven. And I think one of the reasons also that we're not making money is that a lot of the applications are really related to mostly not creating growth, but basically reduction of costs. Majority of people are using AI techniques, or in sense of you wanted to have five lawyers, you're going to use one lawyer. You wanted to have this, you're going to use less. But they're not creating new venues of growth, of opportunities, or new money, or new generation. I think this is one point that needs to be taken into account. So if you take all the companies today which are in the realm of AI, they're burning much more cash with the realm of we want to grow, and once we grow and once we stabilize, then we'll see how we make money. Yeah.
Thank you so much, Mr. Waman. The Muhammad added, you mentioned the Algerian telecom companies can't adapt these technologies because they are not profitable yet. Can you elaborate, please? So I guess,
So
yeah.
I never said this. What I said is on the 5G systems, not the Telecom GPT, today we are not basically able to make money out of the IoT part, because basically the way we provide subscription to people is based on data packages. On the IoT front, which is what we call the things, in general, you cannot make people pay on the data because IoT is twits. And so people are just sending twits. That's it. I'm on, off. It's your washing machine.
Yeah.
The garbage is out, it's in. And so you need to come up with new ideas on how to monetize those things. For now, the interface of telecom and AI, I think there's a lot of money to be made. Why I'm saying this is that a lot of the operators today have been selling packages which are either voice or data, or basically some TV set or channels that you see at home, but they haven't been able to really sell at the moment computing capability. So a lot of things are related to inference. Today, when you want to do inference, especially in Algeria, you don't have much places where you can run your system. Not necessarily training models, but you're in a startup, you want to run your application. And today, what you're going to go is to go through AWS or a company which is outdoor. Now, if Algeria Telecom could provide you a package where you could run those applications, then basically you would get basically a package where you would consume a certain number of computing hours. And I think that's a lot of money to be made. We're seeing it more and more. And why I think the telecom sector is the one which is well suited is a lot of the computing that is required for many applications that we're seeing in the future related to VR, avatars, e-learning, where things has to be speed up to feel the sensation, requires low latency. And low latency means it has to be done at the edge. You're not going to go very far, and the operator in general is the closest. So I think there's a big opportunity for operators to make money if they invest in having GPUs on their infrastructure.
Thank you so much, Mr. Marwan. Now I have a question from my side. Yeah, I'm curious about how the team of Telecom GPT demystified the challenges of telecom dataset, and how they introduce it to and used it to for Telecom GPT training. You mentioned signal datasets and a lot of very complicated or complex data sets related to telecom field.
So on the Telecom GPT one, it was quite easy. We just scrapped on internet all the data that you can find on different website of companies. We didn't take private data because basically you can also fine tune it for given operator afterwards, which is the thing we're doing at the moment, by the way. But then this is like a private kind of models that you build. So we just scrapped more the massive data that you can get related to publications, which are very related to the telecom sector. So in general, you use tools for that, like Common Crawl and others, where you scrap all the internet to get basically those very specific data. You clean them, and then you take a foundational model, and then you fine tune it with that. But then the real value goes even higher for this Telecom GPT is when, of course, you go to a given operator like Mobilis and tell, hey, I want you to give me your inside data because you have been having a lot of calls, a lot of reports specific to your kind of devices, because that's what you sell to your customer, your Wi-Fi routers. And I want to fine tune it for you and it's going to be a tool which is going to be inside. And that's a lot of things. But in general, for that, since it's private data, it's going to be a model very tailored for an operator. You're not going to have like across things. For the RF GPT, what we did, of course, is do measurements were required for 3D configuration. As I told you can't do so many measurements, I mean, unless you have huge money to do campaigns of all the different measurements that you do. So in general, what you do, you go resolve to basically what we call 3D simulators. And these 3D simulators are what we call ray tracing, which provides you synthetic data. By the way, today you have to know one of the big markets, especially for students of l'École supérieure d'informatique, in which we're seeing a lot of acquisitions, are basically your capability of building basically synthetic data. So if you are able to provide, so when I mean synthetic data, it doesn't mean GenAI data, okay? Because if you train a model on generative AI data, then you have something called a model collapse. It's not going to work. So what you need to do is, of course, do things like physics informed digital twins. And you have a lot of acquisitions today which are based on that, because we're lacking data at the moment.
Okay, thank you so much, Mr. Merouane. Um, I have another question. Can you hear me, Mr. Merouane?
I hear you very well. I hear you very well. Yeah, I hear you.
Yeah. I think you were lagging a little bit. I think there is an internet issue.
Okay. I hear you very well now. You
Yeah,
hear me?
okay.
Yeah.
My question is, how does alignment tuning with... Can you hear me, Mr. Merouane?
Yes, I can hear you. Yes, yes. I hear you. Do you hear me?
Yeah, a little bit. I think that there is a latency. Um,
Okay, I don't know why. Okay, I hear you very well. And without latency, I'm hearing
all
very
right.
well. Yeah. What was your question?
Uh, all right. Yeah. My question is, how does alignment tuning with reinforcement learning improve the model's performance?
Oh, okay. So a model which basically does the architecture that I showed you is what we call a pre-trained model. So it just predicts the next token. That's all it does. Okay. Now, in general, that's not enough, because in general, you're not providing it the values that you want to push in some directions. You, in general, when you build a model, you want it to be basically tailored to some things that you want it to answer. And that requires basically some tuning and alignment corresponding to some direction. Just to give you an example, if you train just the model to be able to uh, be good, you in general build it to succeed some benchmarks. So typically, those benchmarks are typically succeeding in the exam of MIT. Okay, but succeeding in the exam of MIT does not necessarily push you to be able to work afterwards. Clear for everybody? Because basically, it means just that you're good in maths, you're good in physics. In the daily work, how much of you will be using Maxwell equation? There's no possibility. So in general, what you do is that the knowledge is there, but then you need to steer it in the right direction. And that is very important, because steering a person to the right direction is very important, because from the fact that you, for example, come up and succeed in easy, and then you want to be steered in a certain direction where I want you to be excellent in, that requires those kind of alignment. That's what we do to make the models, of course, efficient in how they work.
Okay, thank you so much, Mr. Marwan. Now we have a question again from Muhammad. The
Yeah.
question says, for agentic AI, why we need different protocols, especially that the amount of data or latency is less than we already have?
So again, what I said is the following: for agentic AI, you could build basically agentic AI with the actual basically type of network that you have. But then it's not very efficient in how you're building it. Why? Because, and I give you some example. If you want to do compression, for example, then we realize typically that compression and sending data between two devices is not the most efficient way in how we do it today with the system. Second, that I said is if you want agentic AI, which are managing systems with video, it would take you a lot of time to do it. And you would need to build systems with mobile edge generation at the speed of light. So you would need to do specific systems to do that. And this requires basically to be able to standardize the interfaces on how these two talk. To give you back an example, it is as if basically you were asking your assistant, which is Chinese, to talk to an assistant, which is German. They can't speak German and Chinese. They need to do something together to make sure that they are basically capable of interacting. And so there is a protocol that needs to be chosen on how to do that. In the future, as you know, will be basically different models which will be on the market. Um, Apple may develop its own model. You will have basically Samsung, which will develop its own model, Ericsson, which will develop its own model, and these have to be to interact. So you need basically to discuss and standardize what are the protocols that need to be there.
Thank you so much, Mr. Marwan. Now we pick a last question. Okay, this question will be from me. How difficult is developing a specific model for a specific domain like telecom?
Not so,
Talking about
not
the
so,
domain.
not, yeah, not so much. So compared to foundational models, which for which I showed you the cost, developing a vertical in general requires something of I mean, it's still a few hundreds of K dollars, meaning 400K, 300K. We're talking about that. So it's not so much compared to the numbers you saw before, which were at the $1 million. That's the first thing. Second, it doesn't really require a huge team to do it. In general, you just need maximum a team, I would say, of 10 people. That's it, even less to do those things. So it doesn't require. However, there's a difference between building the model and then productizing it. Productizing it meaning interacting with customers, making sure things. This is where your team grows, your company grows because you have much more clients. You need basically all those guys who make sure that everything is done in the right manner. But the model by itself, it's not a big thing.
Thank you so much, Mr. Marwan, for your time and for your insightful talk. It was really interesting. It was really an honor to have you here in
Thank
AI
you.
Summit organized by School of AI. So yeah, thank you so much for your time. Yeah,
Thanks. Take
yeah.
care and happy to interact with you in the future also. Thank you very much.
Thank you so much. The pleasure is
يعطيك
ours.
الصحة. السلام عليكم. Yeah.
Salam rahmatullah.